and we're going to get started. So we're going to be filming twice. So when you present, move towards this side because the camera is recording like everything from the center stage to the side.
If I'm going to be writing on the whiteboard, will it catch that in the middle?
Maybe it has to be moved a little bit, but I'll be sitting there so I can move it myself. All right, so we are in the last 2 days of lectures of the class, and I've had a lot of fun and I learned a lot as well, and I'm hoping that I was able to pass on the materials and make it as interesting as this can be in a field that is super important right now. And just want to go through briefly through the topics we've explored during the semester. We divided our time between theory and some presentations and paper readings. But the theory, to me, is the most meaningful part of it. And we went through, linear prediction, maximum likelihood, regularization, and kernel functions, Bayesian regression. All of that can give us the foundational mathematics. Then we explore one form of machine learning, which is through Gaussian processes, and we had 2 actually sessions on that, and we saw that can be quite successful for things like modeling some of the formal materials, for instance. So even with relatively simple representations, where you learn the kernels, you can have really good results and do interesting stuff for dynamical systems. And really, this class we're not focusing on sort of translating information or recognizing images just for the sake of recognizing them. We're trying to connect them to dynamics and control. So we do processing of images because we are controlling a moving system, a robot, a machine that needs that for creating a policy. And then we did a little bit more of exploration of optimization methods, and gradient descent methods, and Newton methods, and all that is important, constraint optimization that can be important to us. And then we move on into what is considered more called machine learning, logistic regression, and then putting that in a kind of layer architecture, like a simple layer architecture, and talking more about the linear operations and the activation functions as unit operations. And that was the introduction to neural networks. And then we found out that Colab is a great environment for as a Jupyter notebook for kind of quick learning and avoiding installing Python 3 and other modules in your computer. Although you can use pip install within Colab as well when you need it, right? And so you can explore how do you do that as well. And then we use that for, we went on to reinforcement learning. The way we did it is we invited Mingyu to show us his environment and start talking about training with reinforcement learning. And we learned quite a bit from him. And then we went to, just for 2 of the classical networks, and one of them is convolutional linear network that was incredibly successful in 2010, 2012 in analyzing complex images and complex information in the images, and that seemed to be like all was needed for deep learning. But then later on we analyzed LSTMs and recurrent neural networks that they're dominant now, and they became even more important than convolutional neural networks. And so one might expect that maybe there is still incredible inventions to be made in the basic structures of machine learning. And hopefully some of us, you guys and my lab and other labs are gonna make an impact in there, or robotics and machine learning. And we put more emphasis on the practicum, and we saw how to train a car. To move in an obstacle environment, and by processing images rather than just knowing the position of the objects themselves. So we wanted to make it more realistic, such that it's useful for you guys for your research. And I'm assuming that the new controls is that before it was like you have an equilibrium point and you go to the equilibrium point. That was controls until machine learning, right? And now controls is like you have pixels and and do something with these pixels. It's not an equilibrium point anymore, right? It's a bunch of points, and you have to analyze each of them, right? So that was the connection that we did with the practicum, and we provided a link to that GitHub repository for you guys to use. We saw some of the new solvers, like what the name was, Tianshu, the solver name. And then what's going on there. We saw the natural gradients as well from Ivan. A nice presentation as well. So there's still activity happening at the level. And also we explore some of the well-known repositories. And the most well-known is MNIST, but of course there are many others that we can employ and we can create as well. All right, Jon is next.
Yep. All right, so my project was about the human state assessment for classification via machine learning. And this is for the bigger project I'm working on in our lab, which is for the human-robot interaction in the future. But for now, we are very at the initial stage of the project, so I'm figuring out how to do all this classification using the EEG measure. So the very first thing, just how does the human brain work? Like I explained before briefly, there are so many neurons we have in our brain, and then analyzing entire the dynamics of the human brain is too much difficult. So scientists have trying to understand human brain using a neural network, but like I said, 86 billion neurons, so it's difficult to mimic it in our current neural network. So what people try to do is a more spatial approach. This is called ECG, or EEG. EEG is basically spatial electrical monitoring of our brain signal. And so it's captured more like a microscopic activity of the brain. And then use those signal, we can do some types of analysis of how human brains are behaving when they're experiencing something or a certain event. So these things we call the event-related potential study. So these are the one example that we tried to do last semester, or last year. This is my colleague, student Andrew. We try to estimate the different states of the human, either you're trusting or not trusting. And then while we're performing the test, we measure the EEG and then do the spectral analysis and then see we can classify sourcing them into the LSTM layer. And then you can see that the accuracy is really, really bad. So there's a reason some of that, because the classifying ERP using the machine learning, I've tried, but deep learning approaches often ignore and bypass the feature extraction or selection. I did the same thing, although I'll feed the spectral bandwidth of the EEGs into the LSTM, but it was not considered as a good enough features to do that. So because the limited amount of learning data, physiological learning is quite burdensome to collect all this data. So because of that, EEG feature selection is highly important, but we haven't done currently. And then also the deep neural networks, or RNNs, are overfeeding the classifier, so it didn't perform well. So I changed approach. So previously, it's been known that shallow neural networks can actually outperform deep neural network, like I said, mainly due to the small size of the training data set, and then too many parameter features make classification difficult. So make it simple is better. But yet we already know that deep CNNs works better than shallow CNN. So my new approach I want to is first, I have to validate the accuracy of the simple or classical classifiers that event-related potential study. And then I have to check to use a deep CNN for the classification, I need a careful feature extraction, and the selection is required to boil down the useful features for the thing. And then shallow CNN can be implemented to feature selection rather than the classification. So those were like my more bigger project goal. And then for this course, I was more focusing on the building of frameworks and then validating using the classical classifiers. So I'm going to show the results of those. So general flow chart of how we do the classification of the events. So we do the DAQ first using the EEG measurement, and then we got the raw, we call continuous signal, or the raw signal of the EEG. And then we do some external artifact inspection. Usually you could do them manually to see if there are some drifting issues or the high frequency noises. And then based on that, we design the filters, high pass filter, notch filter, and the low pass filter, and then push it through to the individual component analysis, which is required to reject the physiological artifact inspection. So like EOG is eye blinking noises, ECG is our heart signal. Even though our heart is located here and eyes are here, those signalers are significantly stronger, relatively stronger compared to the EEG. So we could often contaminate the brain signal, and you can still capture while you're measuring the EEG. So you have to reject those artifacts. And then to reject those internal artifacts, I had to perform something called the ICA, individual component analysis. So those have to go through. And after we applied the ICA, I got the reconstructed raw data, or the continuous EEG signal. And then I clean them, and then generate event, and then detect the events while you're playing the games or something, like when the participants are doing some stuff, or tasks, we record all the events, what happened. So according to that, we get the detection of the events when it happens, and then do the epoch creation using that. So events, and then filtered EEG, or the raw signal, will be created into the epochs, and the epochs will analyze some of the epoch manually first to see is there like distinguishable difference between the different types of events. Because if it's too similar, it's difficult to do the classification. So we'll do manual inspection first. This is all the post-processing setup. When you go into the real-time setup, it's online setup, it's much more complicated. But for now, it's a post-processing setup. And then we do the feature engineering based on our inspection. So like what types of feature will be useful to do the classification of different types of events. And then finally, from the feature extraction, I extract the PST of the epochs, which is an X variable, and then the epochs events, which is going to be our label, and then do the supervised learning, basically design the classifier of using the PST as input, and then do the event prediction from there. So, what's general flowchart? So first, when I go back to that, so external artifact inspection is important. So this is the raw signal. If you just look at it, whoa, what's going on? Because but what we're looking to here, our purpose of investigating raw signal is to reject those three things. Low frequency drifting, you can see some of there is like drifting around here. And the AC power line noise, which is in the US is a 60 hertz noise, so we have to reject that. Also high frequency noises could be come from the electromagnetic interference around your environment, so we have to reject that too by the low pass filter. So first, I reject the drifting issue. So compared to the previous one, most of them is flattened out because I applied the high pass filter of 0.3 hertz. Although there are some arguments about what is the best optimal cutoff frequency you could apply for the high pass filter for the brain signal. Usually for BCI or the human machine interaction purposes, people apply the 1 hertz, which is very robust. But if you want to detect like ERP people, the event-related potential people, they're more conservative about, I mean more purist about the signal. They don't want to alter the signal as much as the BCI people. So they usually, their threshold, or they think their rule of thumb is a 0.1 hertz. But 0.1 hertz, if you apply them, it doesn't get rid of much of the low frequency drift. So I have to compensate a little bit and apply the 0.3 hertz to see, at least it minimizes to drastic low frequency drifting on the signal. And then apply the notch filter to get rid of some of the power line noises. And then, yeah, from EEG you don't see too much of the power line noise, if you see that, and the harmonics of the 60 Hz as well. But so EEG is a little bit more stable compared to the MRI, so MEG, right, MEG. Those kind of things are more influenced by the environmental factor. But the EEG, it looks a little bit more stable, but I applied it anyway because it's a rule of thumb. So after notch filter, you can see that all the harmonics of the AC frequencies got filtered. And then I had to do finally the low frequency noise rejection, high frequency noise rejection by applying the LPF, and also that do the resampling of the data. And then finally, these are the raw data. We're going to use it for all those classification. So yeah, this is all we call the preconditioning of the signal for EEG. And then after that, we have to reject the psychological, physiological artifact inspection and the rejection. So this is a little bit more trickier than the external noise because it kind of have a crosstalk in the EEG, so it's difficult to see which one is actually what's the source of it, right? Is the source of this noise from the brain or heart or eyes? Is it all get mixed? So we have to do some more in-depth analysis. We call the individual component analysis (ICA) to detect and reject the physiological noises. So this is one of the component that I can, or epochs of the noises or artifact I'm expected to get filtered. So this is an EOG artifact epoch detected by referencing EOG channels. So we have an EOG measurement together with the EEG. So that's why I reference the EOG directly to see how much of the EEG channel contamination around those epochs, EOG epochs. ECG is hard signal. We didn't really, I use a public database, but they didn't apply the ECG sensor together with the EEG sensor. So in that case, you have to create some dummy ECG by running the algorithm that with all the ECG library that people have, and those are the created the ECG epoch, artifact epoch, we're expected to find, okay? And then, individual component analysis basically look into all those ECG channel, EEG channels. We have 60 channels of EEG, or 59 channels of EEG. And then, by comparing each channel, we try to find out what's the principal components, or what's the principal components of those channels. And then those principal components are built up or boiling down into the individual component, which is a little bit constructed between the principal component. And then I can set how many components I can get from it. Of course, if I put the lower number of components, I get the lower numbers of the individual components, but there are risks. So increasing the number of components, of course, increase the computation power, but you have a more chance to capture some of those artifacts or individual components of contamination of the artifact sources. But if you have two lower components, then you could not find it. So I gave a 40. So in number of components has to be lower than the channel. I have a 59 channel, so if I give a n component, 40 is pretty high, to be honest. But these are similar to iLink EOG signal, so which is very easy to indicate. Even just with a component number of the 5 or 15, I could clearly distinguish it because the EOG is closer to the brain. It's very easy to distinguish using that. But the heart is a little bit far away from the brain, so it's relatively difficult to detect. So that's why I increased it to the 40 to reject the ECG signal, basically. And then the algorithm went through the 1,000 iterations to find all this individual component. And from here, now we do something called the Pearson correlation. It's a Pearson correlation-based adaptive z-scoring to detect which individual components are most similar or have a correlation with the artifact they're really looking for. So these are R-scores basically calculated throughout the entire components, individual components are calculated. for EOG, referencing the EOG channel itself, and then ECG for the dummy epoch we created. Okay, so first one, like I said, the individual component 0 was very close to the EOG. You see the score is almost getting close to 1. Sign doesn't matter because it's foot. Okay, so but the ECG, we could detect the 2 individual component that we think it is the ECG, but the score is relatively low compared to the EOG because it's more difficult to detect. And then I had to do the manual inspection, PSD and all the stuff. For EOG, it's pretty apparent. You see all the contamination with the frontal channel. Basically, the eye blinkings gonna more contaminate the frontal channels of EEG. ECG is more like dispersed around the entire brain, so it's kind of difficult to see. But if you combine those together and then map it together, compare with the other epoch. So these are EOG IC, the individual component we found it from the Pearson correlation study, and then comparing those EOG epoch we created, it's pretty similar, which is good detection. ECG, it might be not exactly similar, like I said, sign could flip, but it's relatively, I think, relatively correlated compared to that. Of course, by adding the more sensing modality, like a MAG or some others, you could improve this type of physiological artifact detection. But if you're using the EEG only, what best you could do is what best you could do. Okay? So that's the result of finding the EEG IC. And then this is the before correction of the raw signal, which is very noisy and all the drifting, and then after correction, I have a very nice clean raw EEG signal. So now we call to have a clean raw EEG signals, and they're ready for all types of the feature extraction. So first, before we go into the feature extraction, I had to create the epochs of the continuous signal. So I had to do the event detection. Event detection is relatively easy. Basically, we had to reference to all the stimulus that people had done while they're playing their task game, and then those are plotted. So there are 6 events, but it's kind of difficult to do the classification of the 6 events. It's kind of very difficult. So I decided to simplify and classify basically auditory signal event versus the visual event. Okay, so we have a total 144 visual events and then 145 auditory events. So those are going to be
that's the test data set. That you're trying to classify these from the test data set, right?
Yeah,
so what is the test? What was happening?
This is the entire signal. I of course I also split them to the training data and test data set.
Right. But the training data set, what was based on? What was being shown to the human, or what was the human doing?
So basically, how it works is I create all the epochs first, relevant to these events, and then.
No, what do these events? What do they mean? What does it mean? Button press. The person was pressing a button. It is known that the training set corresponds to the person pushing a button.
Yes.
Okay, so that occurs, and then a smiley means that the person smiled or is looking at the smiley face.
Right.
All right. So all of these things are known to happen in that training set.
Right.
Which is one person.
Right. One person.
Okay.
I don't think there are other publicly available accessible data.
And then this has been this training set. Has it been classified before?
Classified before using different types of methods.
Successfully.
Yeah.
So you already know the results.
Right.
Okay.
On their website, their classification accuracy was 67%.
Okay.
I had a better one than that.
What the website provides this?
This is the MNE. I have a data set they provide.
MME?
MNE.
MNE.
It's a Python library package they have for the EEG and the MAG purposes of software.
Okay.
I use one of their example data set and then try
Okay.
to construct my framework. So these are the epochs generated, and then I do the manual inspection of the epoch first, which is the auditory epochs and the visual epochs. I can see that all the spectral analysis is pretty significantly different if you see all those spectral mapping and then also the GFP.
When you say spectral, what do you mean?
These are the density of the power that how much of the rays are activated or not.
So it means the amount of potentials.
Right, the power of the signal.
Okay.
Throughout the region, different channels.
The
right.
geometry of that
Right. So
potential.
auditory and visual, if you see them, they are pretty distinguishable even from your visual inspection. Right?
Okay.
So
Yes.
you have a higher chance to get classification. And then also I checked all the mean and the variance of those signals, all the average of the epochs, and you can see then auditory versus visual, there are some different patterns that we can recognize it, right? Even from the visual. So it's hopeful. And so I do the feature extraction and the learn classifier using it now. So classifier learning, so X is the PSD of the 5 frequency bandwidth, delta, theta, alpha, theta, gamma, which is very commonly used across the neuroscience study. And then Y is the event label, of course. And then the classifier, I've tried the 5 different classical classifier people are using. The random forest, K-nearest, KNN, LDA, Gaussian process, and then MLP. Before I expecting MLP might perform well because of the neural networks, but surprise coming. The classification result, if you see them, random forest and then LDA perform the best compared with all the other methods with the accuracy of the 81%. But KNN, Gaussian, and then MLP didn't perform as well as I expected. I mean, KNN, Gaussian, and MLP. Especially when I'm surprised with the MLP has only 62% of the accuracy compared to the others. So, but I haven't explored extensively about the hyperparameter optimization. I play around a little bit to make it MLP and then Gaussian process better, but it didn't. I don't think I had invested enough on my time to make it better. But the KNN, I realize, is not sufficient enough to do the brain classification. For the muscle classification or EMG, KNN actually works pretty well. But for EEG signal, I don't think so.
So you said that other studies they accomplish like 60%. So are you outperforming other studies?
So one of the example on the website, yeah, I outperform one of them.
Okay.
Well, these two are these three outperform than the example that's showing on the website.
Okay.
One of the usually the classical method people using the accuracies they're swinging around from the 70% to 80%. So this is actually not bad. It's relatively comparable with those researchers. But I think we could improve even further if you do the more further study and the feature selection.
This is very impressive, right? So you get data and you know if a person is watching a smiley face or is hearing something.
Yeah. I'm happy. Actually.
I mean, this is amazing.
Yeah, last year my accuracy was 50%, so I'm happy. I'm really happy with this result.
You're literally reading thoughts here.
Mind reading.
Yeah, you're mind reading, absolutely.
Yeah. So conclusion, according to literature, hyperparameter tuning doesn't really have a significant contribution on the classification accuracy. So what I need to more focus on is the feature study and the feature engineering to improve the accuracy. And then I had a difficulty to differentiate between the left and right auditory. If you see the event before, I had the left, right of the visual and auditory event also. So visual versus auditory, if you guys saw the signal, it was pretty distinguishable, right? But the left and right was much more difficult. So accuracy of those actually, when I run it with the random forest, it was 57%, which is pretty low. So I want to improve it more than that. So I might explore in the future. So future works, like I said, when the more bigger goal of this project is applying the deep CNN in the future. So to do that, I have to do I want to implement the regional network flexibility. I still want to do that to the more boiling down and then actually mimics the brain dynamics of what's going on between the regional of the brain. And then later, and fuse them into the 2D spectral map or topo map of the brain, and then use that put into the 2D CNNs to do the classification. Something like that.
You should wrap up because we need to have.
So finally, I want to thank all my like advisor, my PhD students for helping me, and then my undergrads. Thank you. Questions?
My final project. So it's titled Sensitivity and Robustness, Classic Control, and DRL. I'm trying to compare, and I'll walk you through what I worked on this semester. So again, the motivation that I started with was that this concept of robustness and sensitivity. And so, any agent in a world or in an environment is dealing with this world that's like constantly changing. And so robustness is essentially like, how can you come up with a control law that accounts for variations in the environment? So like, here's some like, dynamics equations where if you parameterize F, a nonlinear system with like some M, some rho, some inertia, and those physics parameters particularly were random or like sampled from some distribution, right? How could that control policy, which is a function of state, account for those changes? And so I went through a couple steps to set up some analysis. And so today I wanted to walk through this adversarial environment that I created, this ML software tool chain, and then actually some experiments on an adversarial environment, how I could incorporate some robust control theory, and then some lessons learned. And it was kind of a lot of work. And like every time I was develop something, I was like, oh, I could add this, I could add this. So there's plenty of next steps that could maybe turn it into a paper or something. Okay, so first thing is to understand what an adversarial environment does, and particularly in context of like an OpenAI gym environment. So we have like a training loop, right, where an OpenAI gym environment is made with some environment IDs. We have like cart pole or Acrobat and some environment configuration. And a training loop typically looks something like this, where we're in some total time steps. The observation is essentially like the state vector, right? Gets reset, and then we play that environment for an episode. And every environment step, accumulate a reward, accumulate a reward until we're done, and we optimize the model. So the first thing, so here are just some examples, right? Like here's like cart pole, and so the reward here. So this will be like the example that I use in this presentation. The reward is +1 for every time step, and an episode is 200 time steps, so a maximum of 200 rewards. This was a Majoko physics-based environment that I never actually got to because it's much more complicated, but something that I could work
You're
through.
using a +1 every step.
Right.
When do you get +1?
So so it's done when the pole falls, and so you'll see this environment resetting.
Oh, if it hasn't fallen, it's a +1, basically.
Right. If it's gone out of some range, then the environment is done.
Right.
Or the episode is done. And so that episode will now have, like if it's only gone 46 steps, that episode will be, will have a reward of only 46.
Mm-hmm.
Does that make sense?
Yeah.
So.
But what is the optimization happening here?
So this is not real good, right? This is like optimized,
okay.
like, yeah, this is like just like a general structure, right?
The number of total time steps is the number of episodes.
No, it's interesting the way to do it. It's actually the number of total time steps, which is like a way that OpenAI or stable baselines is implemented. You pass it like, I want to run this training for like 10 million time steps.
Yeah.
And the number of episodes is variable because it could end at 50 time steps or it could end at 200. So it's actually just the number of time steps, not a number of episodes. Which there's probably some design consideration that
You could consider all the things, right? You could say the number of steps plus how close it has remained to the top or something like that, right?
for what determines an episode, you're saying?
No, the reward, right?
Oh,
You're
right,
rewarding that
right.
It doesn't fail.
Right.
You also reward like it stays also within a range or something.
Yeah.
Okay.
Right. So if we look at this cart pole, it's just like parameterized by like it has a gravity constant and L for the length, the mass of the pole, mass of the cart, which all kind of gives rise to like how the pendulum reacts or how that environment is stepped, right? So the first thing is to create this adversarial environment with these environment configurations where the physics parameters are modified by a percentage specified in this distribution. So for example, if I've passed a uniform distribution of -0.8 to 0.8, then the gravity term will get sampled from that. And let's say it picks a -0.8, it'd be 1 plus minus 0.8. So now my gravity term will be 20% less, right? So the whole point is that every time the environment gets reset, these physics parameters get updated. So
At the beginning, it's not like they're constantly fluctuating.
yeah, every episode reset. So not like every step, but like so it's basically like an NPC would be like every horizon, these physics parameters get set. So it would kind of look like this. If I had an environment, so I created this cart pole adversary with a uniform distribution. I go and specify the these ranges. Every environment reset, this length. So this big length is nominal, right? And so these environment, so episode resets, changes configuration, changes configuration, changes configuration. And so for control policy, for a single control policy to control like all these different configurations is like what we would call a robust control policy, right? Okay, so now that we have like these adversarial environments, the next thing I developed was like this tool chain that trained, evaluated, did some dimension reduction, and did some visualization. So I could pass the parameter distribution, train it over that distribution of parameters, evaluate that trained model either over the same distribution or a different distribution. And then the dimension reduction is like, essentially I was asking the question, which parameters are significantly contributing to the episode reward? So is it like the when I change mass, is that more significantly affecting the episode reward or length? And then I wanted to do some visualization to actually see it. So the training, so I set up this pipeline where I have this like YAML file where I specify the experiments, train it. It's pretty easy to use stable baselines with the PPO2 model and MLP policy, really thin, or a really lightweight network, like just 2 layers, 64 neurons. It's actually pretty fascinating, right? Like these image recognitions are like thousands and thousands of, or hundreds of layers, and this is only 2 layers, right? And then, so we train, we store the model, and then in some log file, we store, the link to the model, the environment configuration, the training. The evaluation now takes the trained model and evaluates it. And so it runs those episodes. And so it creates this big pandas data frame where on each row is an episode with the different parameters and the episode reward. And essentially like now you have like, a large data frame of all of your episodes run. And then finally, second to last, this dimension reduction. So I found this pretty nifty tool or scikit-learn package, this random forest classifier, where I take, so if I classify where this is my X and this is my Y. And so the classifier has like 200 outputs for 200 states. Then I could visualize which features of the classifier contribute to the episode reward, like the Y value, which was pretty interesting, which I'll show. So the goal here was to find the feature importance, right, which is the parameters.
But you have to specify the number of dimensions in reduced space.
Right, so in like cart pole, there was like 4. There was gravity, length, mass of the cart, mass of the pole. Does that make sense?
Okay.
Right, and so I'll show an example. And then finally a visualization. I wanted to see like these parameters together. So like in a 2D heat map, right? If we have all the range of parameters on one axis and the other axis, we could start to see like the regions and or a surface of where episode reward is high or low. So all together, it looked like this. And so I'll run through an example, but so basically we get some feature importance, and it's kind of hard to see, but here's length, mass cart, gravity, mass pull. And those are like the contributing factors to the reward. And here's like a heat map, which I'll run through an example of.
So the length of the bars.
Yeah.
How much they affect the.
Right. Yeah. Right. So they're normalized to 1.
Yeah, and so for this feature importance, you said you got this from the random forest classifier?
Yeah.
Okay, that's interesting.
Yeah.
Yeah, because like I've seen like feature importance or something like that, or like something like Fisher score or something like that.
Like I think it's the same thing, right? It's information gain.
Wait, so is the Fisher score?
No.
Sorry.
Is the Fisher score?
Yeah, and it's really easy to call.
Is it Fisher score or is it?
So you just call like rf.feature importance. And so I think this is analogous to like in the last layers of the neuron, or and like if you had a neural network, you would find it'd be like the weights of the final, or no, wait, no, that would be the beginning, right? The weights of the larger ones for the final, for the output. Does that make sense?
I've just never seen it with a random forest.
Yeah, it's kind of like a PCA would do this, but then it would be like a linear combination of the inputs. But I wanted like each input individually. Okay, so let's go through an example with this carpool. Okay, so specified. So now I'm able. So now that I set this pipeline, I'm able to like run something through it, right? So we set up the carpool. We set up the number of total time steps. We train on just nominal, right? So we're training on like the nominal configuration, but we're evaluating over the range. So we've trained on like no perturbations and we're evaluating on the range. And we run everything through the pipeline. And so, the mean score was 143 with a pretty large standard deviation. And so now we find the parameters, which contribute. And it's difficult to see. Like here we can find these surfaces of gravity and length. So now like these regions are more susceptible to like failures and instabilities, as opposed to these regions where it's always successful. Similarly to mass cart and mass pull. Well, they're about the same. So like varying these parameters isn't really giving any sort of difference. And then mass of the cart, mass of the pull. And then with gravity, as gravity's varying, and this was pumped gravity up pretty high, we can start to see like where gravity and mass pull, where which regions of success or failure. And so I ran another. So here now I trained over the distribution and evaluated over that same distribution, but I didn't really train for that, long enough time steps. So I only trained for like 10,000 time steps, and I evaluated. There's just 1,000 episodes, and so here you can start to see that. Well, you haven't really like the neural network model hasn't hasn't like successfully solved this problem, because in many of the regions are still failing. So
But you said that you have trained over the whole range.
right, but it wasn't enough episodes, or it wasn't enough time steps.
Oh.
So it found like it first found success like in just these regions, but it wasn't like enough time steps, right? And so so here I bumped up the time steps by, so now I have 100,000 time steps, and I was able to start getting success. And so really, like, these are just 3 examples, but I was thinking like as an ML engineer or like a control engineer, you can use this pipeline to start to tell where you're most like where you're most sensitive and like which combinations or which regions and which physics parameters like give important or are more important to contributing to success or failure. So here's kind of where I spent like the majority of my time was like setting up this pipeline and so I still have like quite a bit to do, especially taking to a more complicated example. So next, I thought to incorporate some robust control theory.
You could do the same study on not on a machine learned model, but on a controller. Right?
Yeah, exactly. Which is exactly what I think that's what I was doing. yeah.
Apply this pure in the word. What I mean is like, did you apply any kernel to this?
Ooh, that's a good question. Did I apply any kernel? So I just like did really I copied a tutorial that showed how to fit a classifier. And this is interesting because it should kind of be more of a regression, not a classifier. But because there's only 200 reward steps, you could classify to all those 200. So I guess the answer is I don't really know. But like this kind of, this like dimension reduction and feature importance is really interesting, I think. So it'd be interesting to see like if there was any better ways to do this.
If you don't do that, you probably see some theory problems.
Somewhat, sorry.
For this one, we don't have too much of the features that will be problem.
Right.
So it's a huge problem.
So it's something, so like, I've never worked with a humanoid or a quadruped, but there's probably like 20 or 50 or whatever.
Right.
And it would be really interesting to find like, like on a quadruped or, okay, now I'm kind of speaking out of my domain, but like if the length of these things changed, how significant is that to the reward, right? Or, really, so that's what I was after with these visualizations was like, is it a combination of these two? Like, is it like this length and like the moment of inertia or whatever, like that, so in this heat map, it would be like a line or something like that. That was like a combination. Right?
I tell you, in robotics, the biggest problem is not the uncertainty of the physical parameters, it's the actuators.
Right.
That's what is difficult to deal with.
Yeah.
The latencies of the actuators,
That would be
extinction, another phenomena that you don't know where it comes from, the sensor themselves.
Yeah, and so this, like, the way I did this was just physics parameters, right? But I think you could also use this to so now you had like your input force for this range. And actually that was an option. I just didn't do it. But yeah, your input force in a range, and you see like how sensitive you are, right?
Yeah. All of these PID controllers, it's really a plug. They're useless. It's like it's technology from the 1920s or whatever, and they need to be replaced by data-driven approaches. So
yeah, and so that like if you can't tell, my whole motivation is like, okay, what, like, how do we start evaluating some of the data-driven methods, right? And then, okay, so cutting to the robust control, right? So nothing fancy. We linearize the system, we get the state feedback, and then I developed this like open gym environment to where now you could set a fixed controller K, and I can't really tell, but it's actually just like stabilizing, right? Okay, so there's this interesting tool in MATLAB that, so now rather than create, the A matrix, the B matrix, the C matrix with fixed entries, I can start to create them with uncertain variables. So same thing, right? Uncertain within these ranges, and then run this RobStab, like robust stability. And this does some interesting stuff that I'm not fully like grounded in, but it does like some frequency domain analysis and essentially finds the smallest perturbation of parameters that's the maximum disturbance. So now like these parameters were varied. It finds within that region the smallest change of parameters which cause the maximum disturbance. So now I can actually set that those values using this distribution, which is like just a delta, right? Like set the parameters to these values and like watch it go unstable. So now like episode, it's like the pole's falling with the same state feedback. And so what I haven't done yet, because this was a lot to set up, was like now is taking these worst case parameters and like guiding a deep RL training in that regime. And like ultimately I want to find like, well, what does this give you? Does it give you like better sample efficiency? Like if you start in the worst case scenario and solve the problem, when you go out of the worst case scenario, like do you have the problem solved, right? And so lessons learned, RL training is incredibly complicated, right? There's hyperparameters not only for the RL training policy, the network, but there's also like the number of time steps, the evaluation. There's like many different methods to evaluate like the sensitivity. Logging is incredibly difficult, right? Like how do I store models, the training information, the evaluation information? How do I like quickly go look up? And then finally, like what I'm after is, which I thought was kind of complicated, is like this correlation or feature importance. And then robust control. Yeah, I'm not yet an expert, but I wanted to take this to like nonlinear systems and start guiding like training, deep RL trainings in these worst case scenarios. And so like I thought I could move to a more complicated environment, like the one I showed, right? More physics, like a real physics simulator, like an inverted pendulum in physics or a double pendulum. And then start to think about like, well, what can we do with control knowledge? Like I said, is there sample efficiency? Like if we start training in the worst case scenario, could we finish the task with like less samples, or excuse me, less like number of time steps? Or could we have some like hybrid system where we know like the deep RL trained model fails in this region, but we know we can like create a state feedback or something in this region. So this is kind of some of the ideas that I was tinkering with. That's my project. Let me know if there's any questions.
So I'm talking about Bayesian optimization to select parameters of a hip flexion assistance device. So I will first talk about what Bayesian optimization is, when to use it, a little background on the musculoskeletal modeling problem, and then a couple examples of how this could be used in practice. So Bayesian optimization is good for expensive to evaluate and black box problems, things that you don't want to actually have to take samples from the real thing too often. And so what you do is you fit a surrogate function or an acquisition function that is something that's easy to evaluate relatively. They're usually smooth because they're based in Gaussian process regression and things like that. So they're not too hard to optimize if you keep parameters under. I've seen people say under 20. I've seen people say under 50, but you can put a few parameters in there and still have it work pretty quickly. And so the thing that's great about this is that it's a trade-off between exploration and exploitation. So actually the reason that this stuff kind of first came about is good motivation for it. If you're digging holes on a very large scale, looking for gold or oil or whatever, it costs a lot of money to dig a single hole, but you got to dig a hole to know what's under there. And so if you, it costs money to dig holes, but digging more holes helps you find the gold. So how do you find the gold without digging too many holes? People also formulate this in the multi-arm bandit example, which is like a bunch of different slot machines and you're trying to find which one's hitting. And so actually Kriging is a name that's just used for Gaussian process regression that this good looking fella here invented. He's a South African mining engineer. And so they call it Kriging because his last name was Krige. And yeah, I think he must have got there, but he was a professor, so he must have, he didn't totally sell out, But so I kind of like this this figure because it shows this dotted. So the Gaussian process regression is the red line and it's fit to all these little circles. Whoops. But the blue dotted line is like a spline that's been fit to those same circles. And so you can see that it follows through, similar path, but like in areas where, the GPR, you can kind of see like how high the uncertainty is. Like, I think that, it's statistically, you get kind of a more, a rich image of what your approximation is of this function than you would with something like a simple spline. So actually another name for Bayesian optimization is sequential Kriging optimization, because that's basically what you do. You'll Krig and then you'll find a point, based on whatever your metric is going to be. You might, if you're trying to minimize this one, you're probably going to pick a point here-ish. And then you'll put that in and then you will Krig again. And so this is a cool little animation that was on Wikipedia about it, but you can see how every time they add a new point, these are showing 3 different acquisition functions. So there's probability of improvement, expected improvement, which is definitely the one that I've seen used the most, and upper confidence bound. So probability of improvement is basically saying, like, if you were to take a slice of this, you'll end up with like a normal distribution. And if you were to go above the highest point you've had so far and then see how much area is left in each of those slices, you go to the one that has the most area in it, because that one has the highest probability of improving. In practice, this one's apparently the least popular, but I saw that there's a narrow case in which it can be really good, which is when you actually have some kind of like a theoretical best case. So if you know what the best case is, then probability of improvement is a good way to go. Expected improvement is based more on like likelihood. It's you basically integrate over all the infinite Gaussian processes that or all the infinite functions that fit the Gaussian process, and then take the one that is likely to get the absolute highest, you want better than the best that you've had for expected improvement. And then upper confidence bound is that one's like 4 or 5 pages of math, but it has to do with what are they called? Sorry, I have notes about this. There's these ideas of cumulative regret and reward, rather than just defining those based on mean and variance kind of outright, like they do more in the expected improvement. But anyway, I went with expected improvement in my stuff. And finally, another really useful asset of this, which is seen in this MATLAB example of a hyperparameter optimization, is that you can use categorical variables in these as well. They don't have to be continuous. So you see, like in this one, they have n on one side, where they had that one was a continuous variable between 1 and 30. And then they also had their distance function they were using for this. It was some kind of neural net, but you can just say you can put these categorical variables in there. So that's a useful thing, and you can see how quickly this converges. Well, it doesn't converge quickly, but how quickly it reaches close to where it's good. So I think, especially from going through all the different MATLAB implementations, it seems like the most popular use of Bayesian optimization today by far is in hyperparameter optimization. But why am I using it? I'm not optimizing hyperparameters. I'm optimizing regular parameters. So an assistive device, you can have all kinds of parameters, especially now that they're getting softer, and rather than just having some rigid linkages with some motors that are mounted concentrically with the hip joint or the knee joint or the ankle, you might have soft bands spanning the body in different ways, creating these moment arms that are hard to quantify, and you can be modulating where those points are at any time throughout the stride. You could have 1 band, you could have 2, you could have 10, and so with these kinds of things, if you're trying to evaluate this in like a musculoskeletal simulation, that's an expensive simulation to run generally, and so if you have a whole bunch of these parameters you want to explore, then this would be a good way to do that. And then also on the non-simulation side, in the scenario where you have to find the best device configuration for a given person, with many parameters to choose from, then this could be a really good way to do that as well. And that's where the paper that I was inspired to do this project from, that's what they did. They had people in there in the lab, and they had a few different torque profiles they could, or a range of possible torque profiles they could use. And then they hooked the people up to a calorimetry device, and we're able to select it in a matter of, I don't know, 18 steps or something like that. So in my case, I have this musculoskeletal simulations, and I really wanted to, so I spent a lot of time this semester working on the musculoskeletal model and trying to get some predictive simulations going. I need to work more with my colleague Wintao, because he's really good at those. But it's been very difficult to do that with models of people that have MS. And so for the sake of having something to present, I just went ahead with the static optimization, which is where you are trying to minimize the total muscle activity over observed motion. So in this case, I'm going to be basically optimizing the passive parameters or the parameters of these passive bands that can be on multiple legs on this person who has a big deficit on the left side due to MS. And so the cost function, I'll go over a couple of examples, but there are measures based on total muscle activation. So yeah, I fought a lot with Java and don't know much about that. And somehow it sits in between OpenSim and MATLAB, which OpenSim is in like C++ and MATLAB's, MATLAB or whatever. And I write code a lot, but I'm not a programmer. So I don't know, I had a lot of Java exceptions this semester. I'm still trying to figure out what the deal is with some of those. But anyway, let's see what we've got. So first, a visual example, because we all like to visualize things. So here we have stiffness on one axis and resting length on the other. And if we just try to minimize the total muscle activation, you can see that pretty quickly it decides that, well, we're just going to make this band very stiff, and we're going to have a pretension length that is very short so that it yanks on the muscles really hard. Because this is not a metabolic model, it's not as punishing for that, because you can stretch it out a little bit on the extension, and then it's got all that wound up energy to help you out.
This is stiffness of a band affects your knee.
Yeah. So it's a stretch between the waist and the knee. But
this is predicted activation.
Yeah. So this is like the average muscle activation for the whole lower body.
You have like EMG and do it progressively, right?
Yeah. So this would be closest to basing it on EMG. Whoops. And so anyway, now we don't get our cool picture because we're using 4 variables, and that's too many axes. But at least we can see. Yeah. But so if you just try to minimize the muscle activity with the static optimization, it's limited because it's going to just want to make very stiff bands. And so one thing that people look at a lot in gait experiments is asymmetry. So obviously the healthy human will walk very symmetrically generally, and asymmetries are inefficient in gait. And if you limp, for example, if you limp for a long time, like I remember an orthopedist told me when I had a knee injury for a little while, he says that you lose something like 50% of the strength in your quad after limping for like 2 weeks or something like that. Like, I mean, it comes back, but it's just like, that strength goes quickly. And so if you have a chronic problem like that, it can be very, very detrimental. And so I took this person who had very asymmetric gait, and I wanted to optimize for symmetry in the muscle activation. So basically all the right side muscles, all the left side muscles, see how close we can get them. And you can see how it, found its way pretty quickly. I was, anxiously awaiting as I was sitting up here, wondering if anything was going to happen, and this huge drop. And then I felt pretty good by the end of these 20 iterations.
This is done with Bayesian optimization?
Yeah, this is Bayesian.
Okay.
Yeah.
And that was in MATLAB.
Yeah, they have a Bayes opt. A Bayes opt thing. And so I forgot to mention it. So basically I had, I restricted these to a sort of realistic set, the parameters. So the resting length could be between 15 and 40 centimeters, or 15 and 50 millimeters, I guess. So no, centimeters, yeah, sorry. Anyway, 0.15 to 0.5 meters. And so you can see that when I did this, it actually like totally, it went for the absolute shortest resting length for the weaker leg, which is leg one was the weaker leg. And then the longest resting length for the stronger leg, which I thought was kind of interesting because the stronger leg, it didn't, the lower bound for stiffness was like 300, and it didn't go down for like the lowest stiffness, but it did go to the longest resting length. So I would like to look more into what's going on there, because that's showing that like it's still okay with having a good amount of stiffness, but it doesn't want to like change that value too much. Whereas in the weaker leg, having that really short resting length means that basically when you go through swing, that's when you're going to have the biggest change in the, like, that's where the pretension is going to matter the most, because that's where like the power spikes, because the band is shrinking quickly at that point. And so I thought that was kind of interesting that that the stronger side band chose to maintain like a smoother like profile, but still with a lot of stiffness. And so then I did one more of these experiments with the asymmetry, but this time looking at the plantar flexors, so your ankles and like basically your calves. And because the kinematic chain of walking, it's all related. So even if you're trying to assist the hip, it's going to affect the ankles. And this actually was able to get like basically perfectly symmetrical as far as the muscle activations went. And this one took more iterations to get there. But and this one was also pretty interesting, where both of them took on kind of intermediate values. So this was an example of like really nicely like ending up with values that sat sort of in the middle of the parameter space that actually accomplished the goal I set out here. And there's a little, when I did the 2 parameters earlier, it pretty much got where it was going to get after 4 iterations. And then this one I did just now, it took like 16. The default in MATLAB is 30, but I didn't see any that hadn't settled down by then.
30 evaluation?
30 evaluations, yeah. So Bayesian optimization is a very efficient way to explore a large parameter space on something that is expensive to evaluate. I need to continue battling Java to get this where I want to get it, and implement the metabolics, because I think that's where I'm really going to find some interesting things. But I do think this is something I'll definitely look to, next time I end up in a physical device experiment. I really wish that actually this hip flexion orthosis thing. So we had, I was not even a grad student yet when I first like had subjects in the lab for this, but like basically we had these TheraBands, which are off the shelf, and they come in a range of fixed stiffnesses, and then you could also place them at a few different places around the waist here. And if I had been able to implement one of these Bayesian optimization things, you can use it for just simple like decision making. Like they'll use it in UIs sometimes for like computer graphics. Like an example they give is like there's a bunch of parameters that make like a reflection look nice, or like that affect the way that like light reflects off a sphere or something. And if you just give people, 6 different visual options and they select one, then that can you can pare down and reduce parameters. So if you had somebody, you could have qualitative responses that could actually guide your fitting of a device. And that's it.